Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the flow through nozzles. Actually, in the previous video lecture, already have discussed regarding the flow through pipes and flow through branch stop pipes and power transmission through pipes, and now we'll discuss about the flow through nozzles. Actually, the nozzle used to fit at the end of a pipe, okay, to increase the fluid flow velocity. So here also similar concept is there. There is a container is there, a large container, and along with the large container, a pipe is connected to this. A long pipe is connected to this one, and at the end of the pipe, a nozzle is fitted to that. Actually, the total energy you can see when the fluid is flowing through the pipe, the total energy of pressure energy and kinetic energy which consists in this fluid. And coming to this nozzle part, okay, when the fluid is coming out from this nozzle, the total energy is converted to kinetic energy at this nozzle, so that the velocity of the fluid will be come out from this nozzle with a high speed. Okay, so let me tell you, the nozzle which is going to be fed at the end of the pipe. So why the nozzle is fitted here? To increase the velocity, to increase the fluid velocity. Now here also we have taken a container is there. This is the container which consists of a fluid, and in the container we have any kind of fluid you can keep it here, but for that particular things we have taken the water which is present here with the surface. This is the surface level of this water, and here a long pipe is connected to this. This is the symbol for the very long pipe, so that's why there is a cut section is there, and this symbol indicates there is a large pipe is which is connected, and this is the pipe, and at the end of the pipe a nozzle is fitted here. So this is the base of the nozzle, and this is the tip of this nozzle, and this is the converging part is there, and from here the fluid is supposed to come out with a velocity. So this is the velocity small v. This is the small v velocity, and this the fluid which is coming out from this tank. Suppose this is the reservoir what I told you as a, or you can say this is a tank which we have considered here, or you can say this is a reservoir also we can say. Now, and this center line, this is the center line of the pipe flow what we have considered here, and the distance from the surface of this water, this is the surface of water we can say, the distance from the surface of the water to the center line at the inlet. This part, this one you can say the inlet to the pipe. So this one you can write inlet part, and here it is outlet condition, you can say the end of the pipe, or you can say this is outlet. Okay, so h you can see here, the h is the distance from the surface level to the inlet condition. So here is the h, the distance from the surface level to the entry of the inlet condition, and v is the velocity of the fluid, and d is the diameter of the pipe, the l equal to the length of the pipe. So these are the parameters are there we supposed to use for this. Okay, so already I told you what are the applications of this nozzles, why the nozzles is required to increase the velocity, and how the velocity will be increased. Now in this fluid, what are the energies are there in this? So all these energies are going to be converted to kinetic energy. Suppose in this fluid flow we have the pressure energy is there and kinetic energy is there. So the pressure energy also will be converted to kinetic energy at the end of this nozzle tip. So that's why the fluid which will come out from this nozzle with high velocity, so this energy also converted to kinetic energy. That's why the we know that kinetic energy equal to half mv square. So the velocity of the fluid will be very high at this point. So what is the application of this nozzle will be? You can see, if you see the practical application, we have many applications of nozzles are there. Okay, the simple example we can see in the servicing center. In the vehicle service center, you can see the nozzle used to use with to flow the fluid with a high velocity. And along with that, I can say in the Pelton turbine actually, when we discuss about the turbine, there I'll show you in the Pelton turbine, the nozzle is fitted at the end of the pipe. So this for that pipe, actually the pipe is called penstock because that is used to very large pipe. So used to call the penstock in the Pelton turbine. Okay. The second example I can give you here, that is fire extinguisher. So you all may have seen the fire extinguisher. At the end of the fire extinguisher, we have a nozzle type will be there. That means the pipe will be converged so that the velocity of the fluid is supposed to come out from the pipe with a high velocity. So the next is fire extinguisher. Even apart from that also, we can use in many places to increase the velocity of the fluid with high. Again, a simple example as I told you first starting, that in a servicing center also we used to see there, service center, vehicle service center or washing center, washing point we can say. Next, even simple sprayer, any kind of sprayer if you require, we can use the small nozzle in that. Even next I can give the rocket engine also. This is the advanced version I'm telling. In that place also we can use the nozzle. So many places we can use this nozzle. Okay. Now we'll see what is the velocity of the fluid which is coming out from this pipe. Okay. So for that I need to consider some parameters. So these are some applications are there. So now we'll go for the derivation part. So for this I required what are the terms are there here. Now first one, diameter, capital D. Capital D is the diameter of the pipe. Capital D is the diameter of pipe. That's why I've written D capital, and D small equal to dia of we can say the nozzle. Okay, and at the outlet condition. This is at the outlet condition. This is at the inlet condition. So this is dia of the pipe at this pipe total. Now next is here D small capital means area also. You can take capital A. This is area of the pipe, and here small area A equal to area of the nozzle at the outlet condition. Similarly, next capital V. Capital V is the velocity of flow in the pipe. Velocity of flow in pipe. And small v, another one here, small v is there, I told you already. The small v equal to we can write, this is the velocity of the flow at the nozzle, outlet of pipe or outlet of nozzle, you can say. Velocity of flow at outlet we can write. This is already in the pipe I have told you. So this is at the nozzle or outlet you can say. Next, L is the length of pipe. The length of pipe. Anything is there? Next, when there is a fluid is flowing through a pipe, we know that we need to consider the coefficient of friction, that is F, because there is a loss of energy will be there due to the friction in the pipe. So regarding that, we need to consider the coefficient of friction. Coefficient of friction. Okay. Now let's see what are the losses are there. Now here one more is there, H, capital H. H equal to the head, total head at the inlet of the pipe. The total head at the inlet of the pipe. Okay. Now our intention is to find out the velocity at the outlet condition and what are the losses are happening during the fluid flow. So I can write here the loss of head, the loss of head due to friction in the pipe, the loss of head due to friction in pipe. We know this equation. This is about Darcy-Weber's equation, or major loss we can say, due to friction. That is nothing but HF equal to 4FL V square by 2dg. This is the equation for major loss. So here F is the friction factor, L is the velocity, so L is the length of the pipe, and V is the velocity, D is the diameter of the pipe. So this is the normal equation for this. Now we can write what is the head available at the end of the pipe at this point. Head available at end of the pipe. End of pipe. So what is the head available at the pipe? So that one we can write, or we can say at the base of this pipe, at this point, at the base of the nozzle, at this point, what is the head available? Okay, so this one also we can write what? Now what is the head available at this point? What is the head available at this point? Inlet condition. This is inlet. So here I have taken outlet actually at this end of the nozzle, but let's see up to here what is the head available at this outlet condition, or at the pipe, at this pipe base of the nozzle we can say. Okay, so how to identify this one? Now what is the head available at this condition, and what are the losses happen in this during the fluid flow? Then we can get the same one. So the head available at the end of the pipe equal to, we can write the head at inlet, the head which is present at inlet, minus what is the loss, head loss due to friction. So head loss due to friction is nothing but HF, and head at the inlet condition at this point, what is the head is there? That is capital H. So this one we can write capital H minus HF. Okay, now if you substitute this value, we can write the same equation like this one, 4F LV square by 2dg. And remaining losses like minor losses, let ignore that. Okay, so you can neglect the minor losses. And what are the minor losses? Is there two things. One is at the inlet of the pipe, what is entering in this, that is very, very less, and during the flow in the nozzle, this is the convergence. So what are the losses are there? That minor losses, let ignore that one. So what we can write, the total loss at the inlet of the pipe, or total head at the inlet of the pipe, what we can write, now total energy at the outlet of the pipe plus the head loss. That means what I want to tell, this is the head at the inlet, so this one equal to this HF will take it to this side, means minus term is there, we will get plus one here, plus term. So that means H equal to, we can get the total head at the outlet condition. So let me write this one, H out plus HF. Okay, now this is the equation. So this equation how I wrote, now from this here only I have taken this one, head at the available at the end of the pipe equal to head at inlet condition minus HF. HF is the head loss during the pipe flow. So this one again, let's make a box of this. This is the equation. Now at the total head at the outlet condition, what I told you initially, that all this energy is converted to kinetic energy. Okay, so at the end of the pipe, if you see that all this pipe is all this energy is going to be converted to the kinetic energy. So now if you consider this nozzle part at this point, see initially I have taken up to here. Now I'm talking about at this nozzle condition by ignoring the minor losses in the nozzle. So what I can write, H, the head available at the outlet condition is nothing but, that is kinetic head. So kinetic head I can write V square by 2g, V square by 2g. Now just put the value of this H out at this point and HF value here. So what we can write, H equal to V square by 2g plus this 4F LV square, 4F L V square by 2GD. Here D is capital, actually during the pipe flow, that's why capital D you need to consider. So this one you can give equation 2. The starting one you can give equation 1, and here we can give equation 2. Now from continuity equation we know that from continuity equation we can write continuity equation for whom will apply. Now the continuity equation during the flow in the pipe and outlet of the nozzle at this point. So let's do this section. By considering this two section, we can write continuity equation. A into V. A is area of the pipe into velocity in the velocity of the flow during the pipe. This equal to, we can write small a into small v. Area of the area at the nozzle and velocity of the flow at the nozzle, V. So from here we can write what? Now we can find out like the V velocity value, capital V equal to, that is small v, small a into V by capital A. So what we'll do, we'll just put this value in this equation. Which equation? Now at this point, this equation velocity is there. Let's put the value there. So you can write H equal to, this is V square by 2G plus 4FL. V square equal to, again we can write A square V square. Here A square is there again, capital A square will be there. So again in the denominator what is there? 2GD. So 2GD into capital A square. Capital A square equal to pi by 4 into D square. So this one we can write pi by 4 D square. Actually this velocity square is there. So I have written a whole total like this I have written here, and this one and this. Or else we can write separately this one, AB by A square. That also we can write. And finally again we need to write this one. So that directly I have written this. So next step, what I can write here. So H equal to, so let me write in this term, V square by 2G plus 4FL A square, this is V square by 2G dA. Okay, 2G dA. Yeah. So now here let common this V square by 2G. Let's see here. This is V square is there, 2G is there. So let take common this V square by 2G. Let bracket. So what will get here? 1 plus 4FL small a square by dA. This is A square is there, I hope. Pi by 4 D square. Okay, pi by 4 D square. Let's keep it as usual A square only. So here also, because I have taken the A square, so let's write only A square. No need to convert this into this one. So let's write this. After that we'll convert, otherwise if it required. Okay, so this is the value. Now finally what we'll get here? What is our requirement? Finally our requirement is to find out the value of V. This V square we got already. So V square equal to, let me write here, V square equal to, this is small v actually, not capital one. So let me give a small V square equal to, small V square equal to what we can write? Now this is 2GH divided by, this whole term is there, 1 plus 4FL divided by D into small a square by capital A square, we can write, bracket close. Now what is our requirement? We used to find out the velocity at the outlet condition. So this square, let take it to this side and make it root over of this. So now this is our final velocity which is required for us, velocity of the fluid at the nozzle or at the outlet of the pipe, equal to root over of 2GH divided by 1 plus 4FL by D into A square, small a square by capital A square. So because we know that the discharge through the nozzle equal to, we can write A into P. So this is all about the equation. And see, in this condition, actually, why we require this nozzle discussion? Nozzle discussion actually very much important to identify or to understand, the fluid flow characteristics. The fluid flow characteristics. So what is mean by this fluid flow characteristics? Actually, the fluid flow characteristics means what is the velocity of the fluid. One thing, what is the velocity of the fluid, or from this velocity we can also identify what is the discharge of the fluid or the rate of flow, and what is the pressure of the fluid at this point. Okay, and any kind of for applications it is required, this nozzle part is required. That's why we can identify the value of velocity of fluid at the outlet of the pipe. So I hope you understand this theory. This is very simple. Just we need to see what are the parameters are required for this, and what are the other things can be considered, like the measure loss equation, and this head at the inlet equal to this losses. Sorry, head at the outlet equal to head inlet, and this minus of losses. So these two things we need to remember, and remaining things automatically we can identify from here. So I hope you understand. If you're having any doubt regarding this, you can give a comment on the comment box. Thank you all.